I'm very happy to introduce our second tutorial speaker, Larry Paxton.
Well, thanks, Tony. Thanks for the introduction. And thanks to the organizing committee for inviting me to come and give a talk about a subject that, well, I hope you'll find entertaining or at least interesting. And since it's a tutorial, the idea was to try to bring a different perspective to things. And so this is based on my own experience in trying to create a future in my own organization. And of course, we're living in very challenging times, and challenging in many, many ways. And so what I'm going to try to do is provide you with some information about some tools that we can use to look at these problems. So now, first, sort of to give you an idea where we're going to go with this talk, we're going to talk about aeronomy, of course. And the thing to ask yourself is how many more years do you have in your career? You know? Because the part of the question is, you know, why do you do what you do? It turns out that about 80% of Americans are unsatisfied with their jobs. Okay, turns out. Now, why is that? So what we'd like to do is create a future in which people are happy with what they do. They find it fulfilling. And I'm going to talk about what makes things fulfilling and why we want to do the kind of things we do. Now, the kind of things we articulate in our public language about why we do aeronomy is, of course, you know, it's this quest for knowledge. And of course, we also say, by way of explanation, because that's part of the times we live in, oh, and here are the uses for it. Okay? Now, so why do we need to create a future for aeronomy? Is it just good enough what we're doing now? Well, that's what I say. You know, how many more years do you have in your career? If we look out to a 5-year horizon, or a 15-year, or for those people who are students here, who might have a 50 or 55-year horizon on their career, are you going to be attending the same sessions now in 55 years? So the question you might want to ask is one that a senior manager at NSF asked me. He said, if I was to look back 10 years or 20 years ago in terms of topics that were covered, what do I see? And I want to talk about how we engender a community that is able to make transformative leaps in technologies or ways of thinking about things. And one of the other parts of this is, what's the future of science itself? And the reason I ask that is, of course, there's a book called The End of Science. And the thesis of that book, which I think I sort of disagree with, is that we'll eventually run out of things to investigate. But what we may run out of before we run out of things to investigate is people are willing to pay for them. And I think that's the challenge. So there are internal and external forces, social forces in particular, that shape the things we do and how we do them. And I want to share with you some keys for transformation, I think, reasons to believe in a future. So this is an optimistic talk. I want to make sure that you believe that before we get going. And really, you know, because you see, there's a lot of nervous laughter. People are worried about that, I think, you know. And so what we can do is we have the choice of our future. And I'll tell you how to have either a good career or a very good career or a great career. And if I forget to mention that, I want one of the students to ask me that. And I think Andy Nagy has volunteered a copy of his book for the best student question in my talk. So, hey, so let's look at this picture. Just this is a familiar picture, and you know it's sort of fallen out of favor. It was a picture that people used to show all the time. But what I think about is, rather than showing how complicated it is and how, you know, there's all these links to the outside, what I really take away from this picture is it shows the sort of the pieces of the puzzle that we have put together, that we have assembled, we've put in the same box. We've got this jigsaw puzzle that's made up of all of these pieces. And now what we're doing when we talk about things like integrative aeronomy and systems aeronomy, it's not saying, we're not going to get any more of these pieces. What we're going to do is some of us are going to try to put those pieces together to form a picture that makes sense to somebody else. And not only makes sense, and not only is useful to somebody else, but inspires people. so that they say, instead of having to have a 5-minute explanation of what you do, you have one sentence that says, this is what I do, and this is the why of what I do. And people can say, I get it. It speaks to me. And that's a big challenge. And I'm not going to tell you the answer. I think what I'm going to tell you is some of the things I've thought about how we can approach an answer to that. Because that's not my job. It's not to give you the answer, but to inspire you, I hope. So, our current research thrusts, just to go back over the kind of documents that we talk about all the time in the community, in the roadmap, there's some questions, like how does the lower atmosphere affect variability, affect geospace? How do neutrals couple with ions? What are the important scales? Now, if we look back in roadmaps for the last 20 years, we see these same kind of questions. In fact, we see them in the early CEDAR reports. How is the magnetospheric energy converted to heat and momentum drivers of the coupled systems? And then, how is our planetary environment changing over longer time scales? Now, many of those questions are things that are familiar to us, but I would assert that in the lifetime of the people in this room, we can start to really address these questions if we have the technological means and the will to do so. If we look at the CEDAR strategic plan, okay, one of the things that it says in there is we're supposed to encourage and undertake a systems perspective of geospace. We're supposed to explore those properties at the boundaries, where, the evolution of geospace, develop strategies, fuse knowledge across disciplines, and manage, mine, and manipulate the data. So how do we do that? So what I'm going to do is I'm going to offer some of the things that I've learned the hard way in a different community about how we build tools to do that. Now, it says in that report that we're not going to abandon the time-tested means of doing things, the instrument and the cornfield approach. Because, and I mean that seriously, we really do need to have the individual contributors as well as the integrators. Because it's like building a cathedral. You have to have a plan, somebody has to have a vision for the cathedral, but there also have to be people that are the stonemasons, the people that are providing the building blocks for that structure. And so what we have to do is give them a reason not only to contribute, and that means, by them I mean everybody here, to contribute, but we also have to have that protective structure that provides funding to maintain that. Now, in those strategic objectives that you saw from both the decadal survey and from the CEDAR plan, have we identified the why? Why do we do this? What is the thing that is supposed to inspire us and inspire the people that are paying for us to do this? Well, lots of times what we talk about is we explore the upper atmosphere because it's interesting and it has a practical value. We hear that all the time. And so there are these reasons. We want to understand, we want to explore, we want to be able to predict, we want to mitigate the changes. Sometimes we'll talk about security, and then we talk about education, bringing up students. And that's, of course, one of the big roles of the CEDAR meeting. But, are we really able to convey the answers to these fundamental questions? Why we should spend money here and not somewhere else? Because lots of times we look at it as an internal competition. We want to select a proposal that's going to study, waves and tides. Which one's the best? But who's to say that somebody from the outside will say, I don't understand why you're studying waves and tides. Let's go study something else entirely. So we also don't, I think, sometimes spend enough time on why should students want to pursue a career? Why should they set a horizon that's maybe 55 years or 20 years? And what are the open questions that we really need to answer right now? What are the things that are the fundamental questions that are stopping us from making progress? Now, one of our challenges, there's a very interesting book called Don't Be Such a Scientist. And it gives an example of the struggle between the anti-science, anti-vaccine community and the scientific community. And it's clear they talk in different ways. And I'm going to show you some research on that, just one example of that. But it says that communications, that is us trying to explain things to somebody else, is just one element in the struggle to make science relevant. You have to convey that information to people in a compelling form. And so what I'm going to try to do is give you some ideas about how we convey that in a compelling form. Because compelling to us is not necessarily compelling to everybody else. Because lots of times when we think about it, when we go in and we talk to legislators, we try to convince them of something or the need for this program, you see, if they would just listen. Well, so there was a study done on the polarizing impact of science literacy and numeracy on the perceived climate change risks, okay? And the question might be, well, what would you think would be more likely? Would somebody who has a high level of science literacy and numeracy, that is, they understand mathematical concepts, are they more likely to believe that climate change is a risk to humankind? Well, it turns out that's a thesis that a lot of people in the community have, and it's actually been in that paper by Weber down here at the bottom, that's actually investigated and postulated. And so it turns out it was investigated by KN here, and it was published in Nature Climate Change. And so it's a little hard to see in this figure, but the hypothesis would be that as you went from a higher level of science literacy, so here's low science literacy and low numeracy, what would happen is, as you got to be, in a sense, more informed, you would assume you would see a perceived risk that's higher. Well, it turns out that they're not well correlated. In fact, there's a slight anti-correlation. There's a significant fraction of the community that's both science literate and numerate that doesn't accept that climate change happens or is a risk to society. Now, does that surprise anybody in the room? See, I think somebody would say, yeah, no, because that's your human experience, but intellectually, you might be surprised. Because what you think is, if I just explained it better, they would know what was going on. You know, I'd be able to do that. Well, it turns out the reason for that is that there are different kinds of communities. There's these egalitarian, communitarian people, and the hierarchical individualists. They're actually, believe it or not, in social sciences, there are names for these various communities, and these are two sort of representative communities of thought. And so the reason is that, as it says here, I quoted this from the paper just to give you an idea of what these views are. The important thing is for the ordinary individual, the most consequential effect of the beliefs about climate change are the relationships with peers. Now, I want you to remember this peer relationship thing when I talk about some other gushy, squishy stuff later on, okay? And then a hierarchical individualist, and here he gives the example of somebody who works in a refinery in Oklahoma City, so we know who they're talking about. Okay, if they express anxiety about climate change, they're going to be shunned by their peers. On the other hand, of course, the same thing is going to happen to the egalitarian, communitarian professor, English professor, who tells their colleagues in Boston that, oh, this is a hoax, climate change is a hoax. You can imagine, so there is within your community pressure to achieve harmony with that view. And this is documented scientific studies, surveys of 15,000 people or so. I'd like you to take a look at that paper. And so now, the reason is that the ordinary individual depends on peers for support. And they realize that their beliefs on the physical environment don't really affect their lives very much compared to what happens when their peers alienate them. So this is a different way of thinking about how we communicate what we do. Talking to people, trying to explain it harder is not going to solve that problem. So now, it turns out that the conclusion of this paper, one of the conclusions is, a communication strategy that focuses only on transmission of sound scientific information is unlikely to communicate much of anything. My paraphrase of that. So how do we do this? How do we make the experience of what we do real? Okay. Now, the reason why I'm talking to you about all this is, and sometimes it's hard to understand this, is, well, why won't things stay the same? Well, Oscar Wilde once said, a cynic is somebody who knows the price of everything and the value of nothing. I think that's really an important way of thinking about it. We live in the time of the cynics. And in fact, managers even talk about budgets and they say, flat is the new up. Okay? Well, it's like, my brain wants to explode when I hear that stuff. You can imagine what I say in private. I'll try not to, anyway. So here's what we're faced with. There's a continued pressure to reduce government spending. that means that no matter what we do, our environment is going to change. Okay? We need to continue we need to demonstrate a continued value to not only to ourselves, but to the outside world. And there are other areas, we can't just, say, well, hey, if the competition's, 1 in 5, I'll just write more proposals and better, okay? That might be how to have a good career, but I told you I'd tell you how to make a very good or a great career, okay? There's also continued pressure on the discretionary budget. That's the part that's not legislated long-term. It's legislated every year. And competition from other areas within the discretionary budget. NASA, for instance, NSF, discretionary budget. And there are other needs, too. We need to continually be able to reinvigorate the field. It's not good enough that I can guarantee that I could have a job for 15 or 20 years. What about a student who wants to have it for 50 years or 20 years or 30 years? Or how do we bring in new people? And one of the dangers is we start to see, and I'll talk about this in just a second, how do we evaluate how vigorous our field is? And we need to maintain core capabilities. So here's a trend in R&D budget. And of course, the thing you see here is that it's going down over time in real dollars. I mean, in fixed dollars. In fact, if you look at the NSF budget, which is fairly encouraging, Suresh, the director of NSF, said something that I thought was very interesting. Remember I talked about this communication thing. How did he describe why you should do the kind of things he's investing in, which is interdisciplinary research? He says, this interdisciplinary research, which you can see in the areas that are augmented here, it moves America forward by connecting the enterprise to benefit Americans, critical to job creation, a growing economy, and a higher standard of living. Does it say anything about doing great science? Does it say anything about aeronomy in there? Okay. So now, I'm going to introduce things. I got to show some equations, because otherwise Barbara would be mad at me because it's not a tutorial if I don't show at least one equation, right? Okay. I'm going to show actually 2 or 3, but that's okay. Not too many, though. This is a curve called the S curve. It's the logistics curve, and it was originally used to describe population growth. Well, it can describe a lot of things. It actually describes salary growth at places like APL. Okay, and there's different job classifications. This is a relative scale, and I can assure you that if you're looking for a job, it's higher than what you're getting paid now, except NSF, you didn't hear that. Okay, no, just kidding. Well, not really. Okay, now, so here's the deal. So here's what I tell people that work for me, because I'm a head of a group of about 35 people. I'm trying to form a community out of these 2 disparate groups that go all the way from the surface of the Earth all the way out to nearer space, okay? And I say, look, these curves, these are sort of this part of the S curve here. I say, this is your salary for different job classifications. And you notice these curves that, first of all, they all show sort of a nice rise early in your career. This is relative, this is just an imaginary scale here. But as you go up, if you don't take on more responsibilities, you flatten out earlier and at a lower level. But as you take on more and more responsibility, your curve grows. Now, the problem is that to move from this curve, where you're supported by somebody else, to one where you support yourself, to one where you support a team and bring in big programs, that entails a lot of risk. But it's not a probabilistic risk. The scary thing is it's a risk of shame and failure on yourself. And a lot of people are reluctant to do that. And in fact, if we look at the personality types and the management styles of scientists and engineers, that's very hard for them to do. And in fact, the people that are able to move up onto these kind of curves that take that risk have a different personality type that sometimes is antithetical. And I've experienced this too. I have no idea what the hell my managers are talking about. It's like they just are from some other planet. What is going on there? How do we do that? Well, so now, when we talk about changing an S curve, okay, jumping from one curve of evolution of a technology or the way we address a problem to another, this is a transformative process. And so we think about it as here's returns and here's investment. And the investment can be the time it takes you to write a proposal. It can take your career, it can be your education, and what you get out of it. And as you start out, like if we think about our careers, it's really hard at the beginning. We're not learning very much. We're just taking classes. And then we start to become graduate students and enter the golden years of your postdoc where you really think, and your graduate career where you really think you're learning a whole lot. And then as you go on in your career, it becomes harder and harder to make advancements. Same thing happens with technology. But what happens is you see a saturation of returns. In fact, sometimes you'll see that it gets harder and harder just to stay where you were. You're running as hard as you can and you're not getting any further. And in the business world, that's where the investors flee. They decide this is not giving me the returns I want. In the educational community, the research community, people leave the field. Now, if there's another way of going from a different curve, from this curve onto a different one, where you change what you do or how you do it, you can all of a sudden get to this point where you take a hit initially. It's harder, but then you're able to really start to see a big return on your investments. And so new capabilities, though, it turns out the reason why we want to make new investments is new capabilities attract new opportunities. And so the question we ought to ask ourselves is, where are we as a community on that S-curve? And it turns out, of course, we're not on just one S-curve. There's lots of different S-curves in the community. Some endeavors are very mature, and you guys can think about that. Ask yourself, where are you on that S-curve? Are you trying to do new things? There's nothing wrong with that because, of course, sometimes, in most scientific careers, you're trying to make your knowledge definitive. Now, some endeavors are using new technology to enhance their returns, so they're on that growth part of that S-curve. And then there's some that are just beginning to explore what can be done. Now, we've heard a lot about that at the workshop, but there's just two examples are the whole atmosphere problems, like the Strat-Warren problem and the tropospheric coupling, just as an example, and then novel technologies. Those are just two examples, and they're not supposed to be definitive. It's just two ways of thinking about it. Now, the reason why it's easier to say this stuff than to do it is that changing these S-curves is difficult. It takes a lot of energy. It's just like a chemical reaction. There's an activation energy that's required to do that. And there's risk, too. It's not only financial risk, it's personal risk. What if you're not able to do that? The other problem is that transformative technologies are unproven. And when resources are constrained, people are reluctant to take that risk. They're reluctant to make that commitment. And scientists are always, every one of us, what do we do the first time we hear a new idea? Our natural inclination is to find 5 reasons why it won't work, because that's how we've been taught. But what I'm going to ask you to do to enable our community to grow is to, when you hear an idea, is instead of trying to think of why it won't work, don't say no, but say yes, and maybe in the back of your mind you can say but, or maybe, or, but first listen and think not only of the implementation of the idea, but what that implies for the community as a whole. Okay, so now community vitality is affected by a lot of things. There are mission design and programmatic factors, and reductions in funding levels lead to, for example, reduced mission frequencies. Fewer missions lead to increases in cost and risk and community conflict, because when there are fewer missions, everybody wants to fight over them. And it leads to mission bloat because that's your last chance to have that mission. So here's sort of a conceptual diagram, and I want to show you sort of some of the factors that go on in this. That because if you have fewer missions, you want to have them last longer. So that means you have a mission design life that's longer. And that means that costs, of course, rise. So here's sort of an integrated cost. And you notice I drew in here a sort of a golden region where costs sort of per year are minimized in terms of cost versus returns. The reason is that if you design a short mission life, of course, your costs can be quite high because relative to your returns, because of course you've got these fixed costs like spacecraft launch costs and ground segment. As you get to longer design lives, you're reducing risk, so that means that costs for the spacecraft for reliability go up. Launch costs might be considered to be fixed, but sometimes what happens is that as you build a larger spacecraft, because you have to build in redundancy, for example, the mass goes up, and then there's this discontinuous stepwise function in terms of launch costs. So the point of this figure, though, is it's sort of meant as a conceptual thing, is that one of the things we need to do is to increase the frequency of carrying out missions or initiatives. Now, the CubeSats are an excellent example of that. They're one of those things that, of course, speaks not only to our goals as a scientific community, but also speaks to our heart in terms of accomplishing things. Duration of programs also derives risks. If you don't have very long, it's risky. There's again, and it will decrease if you have a little bit of time, to optimize things. But if it goes on too long, the risk increases as well. And increasing the mission cadence, if you have too many missions, of course, the cadence is short. It's also risky because, of course, you don't have enough time to incorporate the lessons learned. But if it's too long, again, you start to see the advent of the S-curve. It just becomes very risky because you don't have the continuity. Now, one of the things that happens, we have to ask is, are low win rates sustainable in all of the things? Now, this was some stuff I had done on space mission design, but this also applies to any things we do in terms of proposals. And win rates, especially if we're looking at a win rate of 1 in 5 in proposals, it means that you have to write a lot of proposals, right? Everybody knows that. But what does that mean to you? Well, it all sort of factors in how much money you have to bring in for soft money, what your salary is, things like the number of collaborators you have, and your overhead. Now, all of those factors, as the win rate drops, means it's harder and harder to do integrative science. It's harder and harder to do the kind of things where you have to talk to a lot of people because you can only afford, not only you can't afford to talk to other people, but you can't even spend much time on it. So how do you do things? And of course, one of the problems is that these dropping in win rates, decreases soft money positions, but it also, the managers tend to view this as sort of a market correction. We got too many scientists. Let's get rid of some of these guys. We'll look at the 80-20 rule. 80% of the contributions are created by 20% of the people. Hey, we just have too many scientists. We don't want to see that, I think. And so this also leads to smaller scope and lower risk proposals. To change this trend, there has to be a reason to fund new activities. Now, the ultimate end state of this is sort of typified by this statue from Easter Island. After the collapse of the society, this is a skeletal figure. We don't want to end up in that state. Now, how do we start to reframe our ideas? Here's Maslow's hierarchy of needs. This is the kind of thing where you talk about why do people do things. There's physiological, you got to have something to eat, you have to, a place to live and so on. You have to feel safe, you have to have a community feeling, and you have to have self-esteem, and then there's self-actualization, problem solving, okay? Now, one of the things that we do when we talk about space weather, we talk about our research is, again, that why. We tend to focus on the what, when, where, and how. But the things that we are satisfied are way up here at the top of that hierarchy of needs. Okay? There's the need that we experience. Okay? But the kind of people that we appeal to in terms of our sponsors, they respond to these kind of needs. So how do we do that? Again, if we seek perfection in our knowledge to the point where, at what point will our ability to predict be good enough that people will just say, I'm done. We're finished with the problem. So again, this comes back to how do we continue to build momentum within the community to solve problems, to form a situation where we can have creativity, spontaneity, we can support problem solving and acceptance of facts and ideas. Well, we talk about security. Well, there's national security. I won't go into this a whole lot. It's a very interesting subject. But one of the things is that the traditional view had been always force on force. You can look at Clausewitz. It comes from the concept that was articulated first in the Peace of Westphalia, where sovereign states and nation states were invested as the mechanism of political and military force. But really, when we think about security, it can be taken as the ability to prevent or survive or win a war. It's really too limiting. What it really means is the ability to act free of outside influence. Okay? Now, why am I bringing that up? Because when we talk about space weather, one of the key issues in space weather for the community that is down on the bottom of that pyramid, the base of the pyramid, they want to understand whether something they see an effect on their systems, is natural or it's caused by humans. And some of the things that we look at in terms of research is we feed into these kind of topics, like the GPS system, power grid, aviation, space flight, and satellite operations. And in fact, one of the first things that happened when the cosmos collided with the iridium was there were predictions for the collision possibility. They come out every day. The thing was, when that iridium satellite disappeared, the first question was it intentional or was it accidental? The problem is the predictions are not accurate enough to determine that. It was only after follow-up, which occurred fairly quickly, that they were able to definitively decide that, yes, it not only was likely, but it really did happen. Now, we often talk blithely about space weather and how we're going to transition things from from basic research to operations. But I'll leave this slide. I don't want to go into the details on this, but you really have to be able to pull the string all the way from research down into the customer base itself. And these guys are very, very refined in their needs. In fact, the lesson of this is that you will never find many of their needs, because to expose your need is to expose your weakness. Again, a fundamental insecurity in humans, but it also happens in systems. So how do we bridge that gap? And I'm going to give you an example of that in just a second. But the way they look at the problem space is you want to be able to determine the difference between man-made effects and environmental effects. And we can help solve that problem. So how do we transfer knowledge from research to the operational community? There have been lots of work done on this. This transition activity is difficult. We have to cross boundaries. Extreme space weather is also a threat. It's an environmental threat. How do we communicate that idea? Because it comes back to that core of security. How are we able to manage our lives? How do we manage risk? And some of the issues that we want to address is, what's the role of our community in addressing this? And what does that future look like? Can we develop tools for adaptation and response strategies? And how do we do that? Because, see, not everybody in this community, or even some of the people in this community, are going to be able to do all of that. What we have to do is reach out of ourselves in order to address that need. We can't just talk about, we do space weather because it's important in national security. There has to be something behind it. There has to be a connection. We also, if we're talking about space weather, we do it because of its practical aspects. We also have to make that case, I think. We can get by for a while, but when money becomes tight, people want to see you put actions behind your words. Okay, so now one of the things I've been doing is looking at how we think about decisions and stuff, and what I've got here is a little bit of a description here. And one of the things that you do when you talk about transferring knowledge is this thing from the symposium conferences, speaker series, thought pieces. This is the kind of thing that we're familiar with in our normal environment. And these are, in a sense, in terms of coming up with outputs, actionable information, it's very qualitative. At the other end of this is modeling and simulation. These are agent-based games, for example, where there is a definitive output for those. And those are the most quantitative in terms of making decisions. In between, there are seminars and workshops, and there are exercises of various kinds. There are these actor-based games. And I'm going to tell you a little bit about what those are on the next slide, in fact. So what we have to do is, again, we have to think about what do we do in terms of sharing information. And our spectrum for sharing information is actually really limited. We have a limited bandwidth for doing that here in this community. We share information right now with symposia topics, and there are some technologies, methodologies for that, but sharing is one of the things. We also can study the results of these things. There's a review process and frame and make decisions, develop the information, explore it, and two axes for exploration are these things called tabletop exercises and seminars or war games. And I'm going to give you an example of what that means. The fullest exploration of the topics is this thing called gaming. There are competitive and cooperative games. A competitive game is one in which there's a winner or a loser. A cooperative game is one in which you work together to solve a problem. And I'm going to give you an example of what that means. But it allows you, the important thing to take away from this is you can test concepts and evaluate new technologies and refine requirements. So what that means is if you're trying to convince somebody that an investment is worthwhile. You say, let's imagine what the world would be like without space weather. Okay, what's the impact going to be on your systems? Are you going to be able to do your job? So let's play through a scenario where you have to work with or without this information. Because right now, when we argue things, we need an upstream solar wind monitor. Well, it makes sense to you and me. But does it make sense to somebody who's in the Pentagon who's deciding on a budget? They may decide, well, you know, these scientists, guys, they think that this is worthwhile. And yeah, it's going to cost $150 million. And yeah, I guess it's okay. After all, it's, you know, a little bit less than one Joint Strike Fighter, you know. But yeah, it might be worthwhile. We want to have a definitive case, I think. So now, how do you do that? Well, one of the things we did is we started out with thinking, how do you gather information? And I want to talk about, I'm only going to talk about this really briefly, of course, and I'd be glad to talk about it with you in greater detail. There's stuff on our website about this. But one of the problems we find in all communities, including our own, is that people are reluctant to share ideas. But they're also reluctant to share the fact that they don't know the answers. Because shame, that idea that I'm going to expose my weakness to you, is a very powerful motivator of human actions. And so what we did was we looked at the psychology of groups, and here's what we did was we set up sort of a workshop environment. And these are the principal elements. That first, an attendee has either they can attend in virtual presence, or they can act or be there in real time, and also in reality. The reason I say in real time is because you can play back through these conferences. But you're able to also access conference resources. This includes things like a digital commons. These are things that people who are workshop organizers, elements of the workshop or seminar organizers, have decided are important and they're fundamental. Now, the reason why you do this is because if you're trying to do interdisciplinary work, how many times have you heard somebody ask a question by saying, well, you know, this may be a dumb question, but, okay. For every person who says that, there are 10 people in the room who didn't ask the question because they were worried about shame by exposing their own weakness. Now, one of the things we do too is because you're in an interdisciplinary environment, you don't know everybody. And so if somebody makes a remark or offers something, we have these attendee profiles so you can sort of understand, you know, where's that person coming from? How can I contact them? Can I establish a rapport with them? There's a moderator that runs it and they have resources. But so what you would actually see, and I'll show you some examples of this, is as you work to solve a problem, the moderator is sort of managing this. There's a rapporteur who's making remarks, copying down the verbal interchanges. But there's a back channel that's enabled by computers that are recording remarks that people make. And when we have this thing called the Roadshow, there are 150 computers that we distribute with this software on it to the attendees of the meetings. We also, in order to figure out who's going to benefit from this, we have a subject matter expert database. And those are where we identify people that would contribute. So here's a very small one here. This is a room where we're solving a problem. All these people here are lined up with computers that we provide. And this person here is a trained facilitator. Her specialty is social facilitation. But what she's worked with for 20 years is people who do science and engineering problems. And so what's happening too is one of the people in the room is recording not only what's going on, but also the organizer is trying to frame questions. And so during the discussion, we send out polls in real time, and they show up on your computer in a window. And it says, you know, these are the 5 top issues that seem to be worth exploring. How would you rank these? What are the issues you think are important? Now you can start to track what people respond to, what they think are important things. What are the real issues? Now, the nice thing about this system is not only is it non-confrontational, but it solves another problem. It empowers people because they feel like, hey, if I make a contribution, for better or for worse, it's going to be recognized. It also flattens it because, and I'll talk about this a little bit later, because you've all experienced this where you're in meetings, and especially if you get around 10 or 15 people, there are typically 1 or 2 beach masters, you know, the big bull elephants that try to dominate the discussion, and they start warring with each other. And if it gets bigger, pretty soon there'll be 3 or 4 people that are warring with each other for control of the direction of the meeting. And so by flattening the system, this enables everyone to contribute, and it recognizes their contributions. So that's the key idea behind this. So this is what I mean by making the best use of our human capital. Make the playing field level, drive the direction by the participants rather than by the organizers. That's the purpose of the polls and stuff. Facilitating behaviors, not dominating behaviors, are valued in this process. Because you build up a reputation. You can see who made the helpful comments, who set directions, who made transformative remarks. Okay, and it also means that this can be asynchronous. That means you don't have to be there. You don't even have to be in the room. Lots of times I'd like to be in several workshops at the same time. You have screens that you can flip from one room to the other. You can watch what's happening in this room and say, oh, the bit rate's a little too low in this room. I'm going to flip and see what's going on in that other room. I can make a comment, or I can follow what the discussion has been. Have I missed anything? And another thing I think is, well, first it enables translation, but it removes many of the biases for virtual attendees. Okay? Now that means not only people that are differently abled, but it also means that we remove those unconscious clues about status and about background, all kinds of things that affect how we use people. Okay, why do we even do this? Well, we want to assess risk. Now this chart is notable for its lack of readability, but here's the idea. You start out with identifying a problem. And remember I showed all those various bubbles that were different stages of exploring knowledge? Well, first we identify the problem, we establish a decision-making criteria, and then you go through assessing risk, identifying options, appraising the options, and you come out with a decision. Now, is the problem defined correctly? Does it work? If not, you can go back to various stages at the beginning. If yes, you implement the decision, you monitor and reassess. Now, in real life, this takes a long time. But if you have a game, you can do this all, and you can demonstrate why it's important to make a continued investment in a particular science or technology. You don't want to be in this situation where you're arguing with somebody that we really need a polar orbiting satellite in order to determine weather in the United States, when somebody is saying, I don't need that, I just turn on the Weather Channel. Okay? I don't need satellites. And there's somebody who actually said that, Anyway, okay. So what do? One of the things is define the problem, build an architecture, do the analysis, and this is a squishy thing, So it's a combination of art and analysis. There is no ultimate solution. This is different than the way scientists think of problems, right? And what we're focused on is, understanding the forces that determine what your solution is. And this permits the use of revolutionary, not just evolutionary concepts, because you're able to say, what if we were able to do this? We can't do it now, but if we were able to do this, what would be the impact? And see, that motivates people to make an investment in that technology. And I've got lots of examples that I can't tell you about. But anyway, that's beside the point. Okay, we're trying to get some of this information out so people can understand. Now, we talked about space weather and its impact. Well, look, it turns out the US is got this plan for assessing space weather impacts. There's a grand challenge for disaster reduction. Now, does this mean that you have to learn all about disaster reduction or all of this stuff? No. What it means is, I'm trying to give you an idea of a mechanism by which this can go into a situation where we start to address these problems. And so these are the kind of things that they want to look at. Oops. But one of the things is they want to promote risk-wise behavior. They want to reduce the vulnerability. And so when we design a game, and I've got lots of examples of these kind of games, what you do is you set up an event or a crisis scenario. And it can be things like aircraft loss. It can be nuclear-powered transformer incidents. It can be regional hazard like transformers and so on. And you collect actors that are going to make decisions. And what happens is you set up an environment in which they do these kind of decisions in real time. They can be driven by computers. They can be driven by models. They can be driven by canned scenarios. And what you explore is the complex relationships between things. And the value is actually quantitative because there are measures of this. There's a thing called DIMEFIL, diplomacy, information, military, economic, financial, intelligence, and legal. These are the levers you have as a state for executing policy. And PMICI reflects how the political, military, economic, social, infrastructure, and information systems are influenced by the user. And so what happens is we use these in an event. And so this would be what an event would look like. Actually, this guy is a local newscaster in the Washington area. There's a facilitator that's guiding the interaction. There's screens back here. And what's happening is these people are making decisions about a hurricane that's moving up through the Chesapeake Bay. And they're pretending that this guy is giving them news bulletins. You know, here's what's happened. For example, the transformer system just went down. I can't read that. Okay? Well, prepare to be disappointed anyway, okay? No, I'm just kidding. I'm just kidding. Well, actually, I'm not, but that's okay. So the idea, though, is, see, this becomes an immediate human experience. It's not an intellectual experience. It's not making the argument better or repeating it or being louder or saying the same thing again and again. It's something that people can understand and act on because they've experienced what it is to be without something or to have something new and different. Okay, so the key here is you're demonstrating the value of actionable knowledge, and they give you insight into choices. Now, there are a lot more words on these slides than I can do, than I could talk about, and it's because I'm trying to provide you with a resource. I hope some of you will look at these things later on and talk to me or talk to each other, even if you say, what the hell was that guy talking about? I want you to start to think about what we're doing, okay? So now, what we can do is, we're trying to build this human capital. And one of the things that's often missed is what are the rewards for doing these kind of things? And so, some of you have heard me talk about things about how what we do has to really appeal to the heart. It isn't just an intellectual pursuit. You've got to get satisfaction out of this. And come back to that number, the 80% of Americans who are dissatisfied with their jobs, and probably 99% are worried about their jobs. So how do you do these kind of things? We have the tools in place. We are able to generate a community online. The purpose of talking about these workshops is to show you that we have the tools in place to do these kind of things, and it's a powerful way of moving forward. So now, how do we do things like getting things into space? Well, this is one of the kind of problems that we talk about when we come up with these ideas. How do we prove that they actually work? Well, TRLs are one of the kind of things that NASA uses as a measure of how far along we are in terms of generating a path forward. There are lots of approaches that you can use to make sure that we get this transformative technology in there. But here's an example. And now I'm going to give you some examples. I'm not going to try to give you a definitive answer because I want you to think about these things. So first, let's consider a rocket. So here's another equation, okay? We're going to write down the rocket equation. And here's the question. How long can a rocket hover at 1G? And as I'm asking you this question, think about why would he ask that question? Okay, so now you write down the rocket equation, and you define I'm going to define the mass in terms of, the fuel and the structure. This is the total mass here. And then here's the mass of the fuel, and there's the mass of the structure, and you can integrate that guy, and you find out this number, tau, depends only on the specific impulse and the mass of the fuel at the initial time to the mass of the structure. And you imagine if, this ratio was basically 1, there's a limit, but the ISP is the principal thing here. Well, it turns out that there have been some studies. Their control systems have been demonstrated. This is a zombie in the lunar lander competition. It went up 50 meters, went across 50 meters, went down 50 meters, okay? Now, how long did that take? And again, why am I talking about this? Well, it turns out you can get about 12 minutes of hover time, okay? With a relative velocity in the atmosphere of 0 at any point in the atmosphere. So imagine, and also the other thing is that when you have ion thrusters, the ISP can be 2,000. These guys have very small thrust. Here's a picture of these guys. They like to put coins in these things, but there's a dime, and these are thrusters. So we can start to think about chipsets. Now, why would you do this? Well, look, imagine you take a system like this and you put it on a commercial or a commercial suborbital or a sounding rocket or resupply flight, and you kick it off at 90 kilometers, 105 kilometers, 140 kilometers or something, and now you have the ability to do the kind of thing we've dreamed about with a 0 relative velocity, put instruments in space above some point at an ISR, wherever. And now you're able to make samples for 12 minutes. Now that would be transformative science. That would be the chance, though, also to reward people, to give them that feeling like, here's something you can do in just a few months, because you're going to recover this payload. You're going to be able to fly it again, especially if you're taking advantage of commercial suborbital stuff. So this is one of those kind of things. Now, the reason why we would do this is that transition region between where a lot of the stuff that we talked about in the CEDAR strategic report, below 140 kilometers, we know virtually nothing about it in terms of in situ. There have been lots of sounding rockets. Miguel Larsen's famous spaghetti plot of all the winds and stuff, we fly through with a sounding rocket. If you go back in the history of things, there are controversies about whether the measurements we made were affected by the relative velocity of the vehicles themselves, like the sharp controversy about the atomic oxygen density in that region. This is a way to start to look at those problems. AEC, for example, which is one of the few things that actually went down there for more than once, it only went down below 135 kilometers about a dozen times, and it did that at 8 kilometers a second. Okay? So now, this is just an idea. I'd like to see if maybe that resonates with somebody. The other thing is that UAVs. Now, the NASA guys, they seem to have no shortage of both ideas and money, but here's a UAV. This is a Global Hawk. And it's deployed out of Wallops. They're portable ground stations. It flies for 32 hours, 12,000 nautical mile range, which means if you think about that in terms of longitude, you can fly out 8 hours in local solar time one way. It carries 700 kilograms of payload. And it can fly at 20 kilometers altitude. So imagine, now, what could we do with that? Well, ground-based instruments don't have to be on the ground anymore. They can move around. There are even phenomena that you can start to track, that you can move with. You can also look at the local solar time variability at a fixed or near constant universal time. This is a plot of backscatter radiance, sun overhead conditions, and this is on the ground, and this is 1 micron. So visible is down in here, going to 300 nanometers or 0.3 microns. And you can see there's a factor of 100 difference in the backscattered radiance. And you can see the effects of atmospheric windows as you go up in altitude. This is 0, and this is on up to 100,000 feet here. As you go up higher and higher, not only does the backscattered radiance drop precipitously, so that would allow you to fly instruments that have lower background, like you might not have to have a triple Edelon to do day-side observations. But if you're able to do this and you've got that 700 kilograms, you can fly these things again and again. But you can also do things like moon-up air glow observations. And you now have a truly relocatable optical observatory. Now, one of the most exciting things we've been looking at, of course, is mid and low latitude connections. And now this is another one of those plots that only scientists love. And I happen to love it myself. I think it's really great. But look, here's the ionosphere up here at the top. And here is all this magic stuff that we love to talk about, right? And here down at the bottom is deep convective clouds. They drive this process. So now, well, what does that mean in the future? Well, we ask these questions like, what are the origins of the structure, in the upper atmosphere, and how do these events evolve? And then one of the things we also ask is, how is it going to change over time? Well, let's ask this. Do you think that it should change with climate as we heat the lower atmosphere? Well, it turns out you can look at the Clausius Clapeyron equation, and you can find out that the occurrence rate of these deep convective clouds should go up by 6% per decade. So will we see more convective instabilities? Will it change the structure of the ionosphere or increase the amplitude of these waves? Will we see more ionospheric instabilities? One way to look at this is this is a map of buoys, current ocean buoys. And the ocean buoys tend to like to be in the intertropical convergence zone, well, also in terms of shipping areas. But here's a region where, again, ground-based doesn't have to be ground-based anymore. Imagine putting dual frequency GPS to get TEC measurements, and we can start to look at the structure of the ionosphere on a global basis essentially from the ground. I just want to cover one or two more things here. I told you you're going to be disappointed, so am I. One of the things that's most powerful in terms of motivating stuff, the thing that I actually started out in my career with was doing modeling. doing two-dimensional, three-dimensional modeling. And it turns out that commercial off-the-shelf graphics processor units can be used for this. And I'd like you to look at this paper that appeared in the Bulletin of the American Meteorological Society, where what they did was they actually ran a model that's based on WRF, a regional weather forecast model, and they looked at cloud simulations. And the cool thing about this is a screenshot, you're able to interact with the model in real time. Because these guys, these graphic processor units that cost only a few $100s, are capable of teraflops of calculations. And they do it natively. So it's not like you have to go to a supercomputer where you have to wait hours or days for it to be post-processed, to be made into a flat plot that you can't do anything with. Now, how powerful is this as a connection to students? The other thing, of course, is that with this, because it's all done in the graphics processor unit, you're able to interact with the plots. You're able to change scales. You're able to take slices through this interactively and display this. And you're able to visualize things like velocity, temperature, and humidity in this case. Another important thing is, in terms of education, you can make movies of this in real time. So somebody who's familiar with this subject can go through a run and flag stuff for people to look at and motivate them to look at phenomena. But what they say, the ancient proverb, a picture is worth $1,000,000, okay? This is, again, a way of communicating directly with people in a tangible way. And it communicates with the students, too, I think, new people, because here's the way that, because the code is embedded in here, Gales is this particular instantiation of this, you're able to interact directly with the simulation. How many times have you wanted to interact and change the basic parameters of a model run while it's running? You can't do that on a supercomputer. You can do that on this. And again, this is a way of communicating directly to people. We've done stuff here like demonstrating MEMS technology. This is a CubeSat form factor that measures ion densities. Little guy about this big. Cool thing about this MEMS technology, replicatable. $50,000 to do the sensor head. Now, I guess I really am running out of time. Okay. So one of the things I would have liked to talk to you about, again, in social stuff, is the rise of autism spectrum disorders. 600% increase. I don't have time for that. I think that the reason why I wanted to talk about that is we want to maximize our human capital. And so what we have here is a choice. That choice between door number 1 or door number 2. Are we going to do things the way we've done it in the past, or are we going to create stone soup? Are we going to take the individual contributions from people and make something greater? Now, you can check out some of the stuff I've talked about on our Gaia website. We've got 2 meetings coming up, a timed meeting that's a workshop on understanding the upper atmosphere. It's going to be October 16th through the 18th. I've got another meeting coming up, the Seasons Conference. This is a classified conference on space weather operations, space weather missions, measurements, and products, say the warfighter. And here's my final charge to you guys. This is a quote that I've tried to live by. It's from Dickens' David Copperfield. Whether I shall turn out to be the hero of my own life or whether that station would be held by somebody else is yet to be seen. That's paraphrasing, of course. So here's my charge to you, right? Be the hero of your own life, no matter what direction that takes you. And remember I told you I was going to tell you how to have a good career, a very good career, or a great career? Good career, do your job, work hard. Very good career, work really hard. Great career, take risks. Risk not only your livelihood, but your concept of yourself. Expose your ideas, share it with people. And that's really hard. Anyway, well, thank you very much.